Okay, so next we look at another stochastic local search method, which is based on population. So the difference here is that we are going to work with a population of candidates instead of just one candidate essentially. We take inspiration from what is happening in the natural world, and if you consider life on earth, there are some fundamental questions that we can ask as to what is life. So this is all a little bit of philosophy, uh, just to set the background for our genetic algorithms. Um, why do we have different life forms essentially? Okay, and is evolution a design process? Is nature trying to design some perfect creatures or something like that essentially? And if yes, then what is the purpose? Is there a purpose to nature? I mean, these are all philosophical questions, and which kind of lead us to thinking about what's really happening in nature essentially. So there's a nice book which I read. It's called Creation, Life and How to Make It by Stephen Grant. Stephen Grant, uh, and this book is about artificial life and creatures. So there was a time about 15-20 years ago when artificial life was a bit of a craze, and people used to have artificial pets, and which were living in the virtual world, and they used to be really attached to those artificial pets, and people would say, I have to go home and feed my pet or something like that, even though it was just a virtual creature. So that was the notion of artificial life, and there was this whole field called creatures. If you just look up this on the net, you will find some interesting stuff. What Steve Grant says that he has uncovered the most important law of nature, and it is this: things that persist, persist, things that don't. It sounds like such a trivial statement, but if you imagine that that's what's happening in the real world. Structures which persist, they persist, and which structures which don't, they don't. So if you think of it in terms of evolution, whichever life form survives, survives, the others don't survive essentially. But he takes it at a much more fundamental level, that whatever persists, by definition it persists essentially. So it sounds like a trivial argument, but it's worth a thought. So things that persist, persist. He clarifies that much of what we see persisting, like clouds on a hilltop or ripples in a pond or even human bodies, are in some way a persistent impression of constantly changing landscape. So in his book, he gives this very nice example that if you are going hiking in the mountains, uh, then very often you can see a stationary cloud on top of the mountain range essentially. But if you were to go to that spot in the mountain range, you would find that there is a lot of breeze happening there essentially. So what's really happening, he says, is that air is rising up towards the top of the mountain, and as it rises, it condenses and forms the clouds, and then it moves on and goes to the other side of the mountain range. The air is constantly moving, but it appears to us that there is a stationary cloud essentially. So what we see as persisting is not really the cloud, but it's the fact that at that place the moisture is condensing and then moving on essentially. So he also says that our own bodies are also like that we are made up of certain number of atoms, and that these atoms that we have currently are entirely different from when we were children essentially. So how do you define yourself or your body essentially? You can't define it in terms of the atoms that make you up essentially, because those atoms, they come and go essentially. But somehow there is a persistent image of a human being. That's true for every object that we see essentially. So inanimate matter has natural persistence, for example rocks and water and so on. I mean, if you ignore things like erosion and evaporation and so on. Life forms have a different form of persistence, which includes growth of bodies and procreation of offspring essentially. I mean, that's what life is all about. You eat and you procreate essentially. Plants and animals consume food, both for adding matter to grow their bodies and for the energies that they need to move around. So, food is basically a source of energy for us and also a source of matter essentially. A living creature consumes resources, both food and energy. Resources are limited in the world, creating competition. Only a limited number of growing creatures can be supported by life on earth essentially. All living creatures die, thus returning matter to nature and making space for another living creature. Where does competition come in here? Species compete for the same resources. For example, lions and hyenas, they compete for the same prey. For let us say they are hunting rabbits or foxes or whatever. But within the species also there is competition. It is not just between species, but it is within the species, and that is what is of real interest to us. Because the fastest or the wiliest foxes get the rabbits, let us assume foxes are hunting rabbits, and the fastest or the cleverest rabbits, they escape essentially. So, you can see that there is competition within the species, and that is where Darwin used the term survival of the fittest. The fastest foxes get to feed, the fastest lions get to feed, and so on and so forth. The others do not survive. Likewise, the fastest rabbits manage to, or deer manage to escape, and the others get eaten up essentially. So, there is a constant competition going on within the species, that each species is trying to become better, and within each species it is trying to become better because the individuals which are fitter, they tend to survive essentially. And it is this competition to produce better designs, if you want to think of nature as producing better designs, that we want to simulate in our algorithms. So, the world of course is a big vast ecosystem where different life forms, they influence other life forms. So, the arrows in this diagram, they are supposed to, it is called as an influence diagram, and essentially, and this arrow shows a positive influence of one species to another species essentially. If you moved in the opposite direction, it would be the negative influence. So, for example, if you look at the population of foxes, it has a positive influence on the population of lions. The more the foxes, the more the lions will get to eat foxes, and the more they would population of lions would increase. The more the population of lions increases, when they die, more the bacteria is supported from there, and the more the bacteria, the more the number of trees that will grow, the more the amount of grass that will grow. The more the amount of grass, the more the number of rodents it will support. So, this basically there is a vast ecosystem which hangs in a delicate balance, and which is why people often keep saying that survival of all these species is important for the rest of the species. So, we are interested in evolution here. So, species evolve continuously, foxes become better, humans become better, and so on and so forth. So, a species is like a design of a life form, and nature has evolved the process of creative adaptation, that how to make that species a better species. So, in his famous book called The Blind Watchmaker, the British evolutionary biologist Richard Dawkins has emphatically argued that there is a ratchet mechanism, basically, which means that every time nature comes up with a design which is working well, then that design persists essentially, that it is like a ratchet mechanism, that it has found that design, and therefore, henceforth all the children of that particular individuals or species, they tend to propagate more and more essentially. So, in that sense, nature has a built-in mechanism whereby it keeps experimenting and then keeps the best designs. That is what we are interested in. Okay, we are interested in candidate solutions, and we will see that we will try to mimic nature and keep the best candidates. So, of course, Richard Dawkins is famously known for the fact that there is nothing called God, and he says that there is no supernatural creature, and all that is happening as a matter of these random events, which Stephen Grant said is basically to do with persistence. Richard Dawkins also wrote this book called The God Delusion. It says that humankind basically deludes itself into saying that there is a God who is guiding us. So, let us come back to evolution. Uh, if reproduction was asexual or cloning, then there would be no change. The child would basically be a copy of the parent essentially. So, that is what we mean by saying that nature has come up with a remarkable mechanism, and in the race for fitness nature has struck on a mixing strategy which is called bisexual reproduction. So, children are always produced from two parents and they inherit features from two parents essentially. So, you can see that there is a mixing of genes that is happening. So, every time two creatures reproduce, the offspring is unique. That is why siblings are not identical. Uh, uh, every sibling inherits something different from their two parents. It is not that everything is inherited from the two parents. So, something from one parent and something from another parent. Now, this French poet Paul Valéry said, describes this whole thing very poetically. He says it takes two to invent anything. So, we are talking of design, for example, we are thinking of nature as doing design of life forms and things like that, or we are designing solutions for a certain problem that we want to solve. So, Valéry says it takes two to invent anything. The one makes up combinations and the other chooses. So, he says that there are two processes which are happening. One is this random mixing up of genes, and the other is competition between the individuals which selects the fittest elements. So, making up the combination is like mixing up genes via sexual reproduction, and the choice of which combination is good is left to nature, where survival of the fittest happens via natural selection as described to us by Charles Darwin. You can see that this is a little bit like generate and test. Generate candidates or generate candidate solutions and test whether they are good or not. In our case, of course, we are interested in a particular goal, but the idea is similar. Now, in the real world, we distinguish between the genotype of an individual, which is the genetic makeup of the individual, and the phenotype of the individual, which is the physical body that the individual embodies essentially. So, an organism genotype is a set of genes that are responsible for a particular trait for that individual, and organism's phenotype is a physical expression of those genes essentially. So, the mixing up happens at the gene level, but the competition happens at the physical body level, because it is a physical individual which is trying to compete in the real world to survive essentially. So, we mix up the genes and the body that results competes in real world essentially. So, it is a physical entity that competes in the real world. So, how does this mixing happens? In nature, selection happens by some form of attractiveness essentially. Mixing of genes does not happen at a random fashion. Individuals in all species, practically all species, they actively choose their mates essentially. So, there is some notion of attraction which is built in, and that somehow results in us choosing mates who we think will give us better offspring. That is the whole idea of improving the design as we go along. So, all life forms have evolved ways to attract the opposite sex. So, male birds, for example, they always put up a song and dance show, the most striking being the peacock that you can see dancing. It is not the peahen which dances, it is the peacock which dances. So, birds have this mechanism of the male trying to attract the female. Humans are more complex. We have criteria like health and wealth and cleverness, and everything is part of a mating game. Now, let us move to genetic algorithms, the algorithm that we are interested in. These were devised by John Holland in 1975 and popularized by his student David Goldberg in his book, which is also called Genetic Algorithms. These are a class of methods of optimization problems, more generally known as evolutionary algorithms. So, this is basically heuristic stochastic adaptive search algorithms essentially implemented on a population of candidates in the solution space essentially. So, the idea is that different candidates will have different components which we can think of as genes, and we are trying to get the best from different candidates, and that is inspired by the process of natural selection. But what we do in genetic algorithm is that we define a fitness function, which is the evaluation function or whatever we are trying to optimize, and we apply that instead of having the candidates go and compete in some real world or something like that. So, we determine how good the candidate is by applying what is called as a fitness function. And then what we do is that we allow the fittest candidates based on the definition of fitness function to go and mate and to reproduce essentially. So, in genetic algorithms, selection is not natural, it is artificial, and it happens as follows: that given a population of candidate solutions, we always start with a population of candidate solutions. The first step is reproduction, in which we clone each candidate in proportion to its fitness. Some may get more than one copy and some may get none essentially. Then we do what is called as a crossover. So, this is terminology that is common to genetic algorithms. By crossover we mean randomly mate the resulting population. So, what did we do? We started with a set of candidate population. We cloned them in proportion to their fitness, and then we are randomly mating the cloned population to mix up the genes. And once in a while we do a random mutation, that we change one component because sometimes especially if the population is small, a gene may be missing and you are looking for a random mutation to improve the species. So, the first step is selection. We said that we will clone all the candidates. So, imagine a roulette wheel on which each candidate in the parent population is represented as a sector. So, the roulette wheel I have drawn on the right, and in this example there are 7 candidates. So, P1, P2, P3 up to P7, but in general you may have population of n candidates, and they occupy a space on the wheel where their angle that they subtend is proportional to the fitness. So, you can see that for example, P6 has a smaller angle as compared to P5. That means P5 is a fitter parent, P6 is a less fit parent. And this mechanism of the roulette wheel is basically you spin the wheel n number of times, and wherever the arrow stops, you create a copy of that particular parent. So, the roulette wheel is spun n number of times. How would you implement this as a program? We want to start with the initial population of n parents and produce a new population of n candidates, but such that some parents will get more children or clones, and some parents may even die out essentially. How will you do this as a program? You can see that you can use the same mechanism that we did in simulated annealing. You can generate a random number, and based on its value you can decide which parent will get a copy to clone, which is in some sense simulating this roulette wheel essentially. The selected parents are added one by one to create a new population, that we have already said, and members of this new population will be now paired and mated randomly. So, now our pairing and mating will happen randomly, unlike in the real world where it happens by attractiveness. Here we are doing it randomly, and then we will mix up the genes. That happens in this process called crossover, and this is a standard term that genetic algorithm community uses. A single point crossover says that take up the chromosome, sometimes we refer to these candidates as chromosomes, and break it up, take up 2 parents that you want to mate, break them up at the same point. So, I have shown one parent in red and one parent in blue, and that arrow shows where they are going to be split. So, you can see that the first child has got some genes from one parent and some genes from the other parent, and the remaining genes have gone to the other child. So, 2 parents P1 and P2, they give us 2 children C1 and C2, and this process is done randomly. We select the 2 parents randomly, we select the crossover point also randomly. So, just imagine if this was a SAT problem of 8 variables, you would produce 2 children, and we will see examples as we go along. The single point crossover is just an example. Any operator that mixes up the genes will do. So, for example, for the same 2 parents, you could have taken alternate genes from alternate parents, and that also would mix up the genes. The idea is to mix up the genes essentially. So, when Kohlberg and Holland wrote those papers, they were trying to see that are there chunks of genes, for example, which have certain good properties, and how can we devise crossover operators so that those chunks are maintained, but we will not get into those details. We are interested more in the algorithm. So, this is a genetic algorithm. We start with the initial population of n candidate solutions. This is just the initial population. It can be randomly generated, or it could be generated through other means. For example, you might have tried simulated annealing or iterated hill climbing or something like that. Basically, you have generated n candidates. You compute the fitness value for each member of this population P, and you create a new set S that with the probability proportional to fitness value randomly select n members from P. So, this is random selection with repetition. You are allowed to select the same parent again and again, that is also allowed. Otherwise, you would just reproduce the original population. Then you split the set S into 2 halves and randomly mate and crossover members to generate n offsprings. That is called the set of offspring essentially. With a low probability, we will see, when we see an example, we will see this need for mutation, mutate some offspring. So, randomly change some genes of some offspring essentially, and it has been said that such random mutations, most of the time they are bad for the individual, but once in a rare while they can be good for the individual essentially. So, there was a story that somewhere in Italy at one point there was a random mutation amongst the people which gave them the ability to eat all kinds of fried food without getting unhealthy. I do not know whether the story is true or not, but anyway, this is the idea of random mutation, that you change some genes randomly and sometimes it works out well. Then we say replace the k weakest member of P. P is the original population that we started with the k strongest offspring. This k could be equal to n also. In the sense, you could replace the entire population also. But sometimes people do not do that. They keep the strongest elements of the original population always intact essentially, because we want to keep the stronger ones there. And you do this until some termination criteria essentially, and then return the best member of P. So, here is an example of this process. We have the SAT formula with 6 variables and also 6 clauses, as you can see, 1, 2, 3, 4, 5, 6, and the heuristic value is the number of clauses that are satisfied, and so it is a maximization problem. So, if these are the 2 candidate solutions, what does this mean? This means that this is A, this is the value of B, and so on, and this is the value of F essentially. So, all the 6 variables have a value of written in this particular order. So, 0, 1, 0, 1, 1, 0 means A is equal to 0, B is equal to 1, C equal to 0, D equal to 1, E equal to 1, and F equal to 0. And likewise, there is the other candidate 1, 1, 1, 0, 1, 0. And you can see that for both the candidates the heuristic value is 4, and I encourage you to look at this formula F that we are working with and see that for both the candidates 4 of the 6 clauses are satisfied. But if you were to do this single point crossover as shown here, then you would get this new candidates, and you can see that one of the new candidates, which is C1, has all 6 clauses satisfied. So, it has improved essentially. So, that is the idea of genetic algorithms, that you mix up the genes of your parents and hopefully you will come up with better candidates also. So, iterated hill climbing, we said, was had a footprint which said that if you started from any one of these shaded nodes, then you would reach the global maximum essentially. So, it really depends on the shape of the curve essentially. In genetic algorithms, we start with the initial population which is random and diverse. So, you can see that the shaded nodes are spread all over the place, and what happens in practice, as we have seen, is that as the algorithm is run, these candidates they tend to cluster towards the different peaks in the state space. So, for example, some candidates are here, some candidates are here, some candidates are here, and so on. You can think of them as different life forms being formed or something like that, but in general they tend to gravitate towards maximum. So, genetic algorithm also is known to work quite well. Let us look at a very tiny example before we look at some more detailed example. This example is also from Goldberg's book. Let the chromosome for a tiny problem be a 5-bit string, and let the fitness function fx, so we always define a fitness function, be the square of the 5-bit binary number essentially. And let us say that there are 4 candidates, we have a small population of only 4 candidates. In practice, it has been observed that for genetic algorithms to work well, we must have a large and diverse population. Why diverse? Because we want all different kinds of genes to be present in the population. If the population is small, then some genes may be present and some genes may not be present. So, we illustrate this algorithm with a single point crossover. So, here we have started with some 4 random candidates, and their binary representations are as shown 13, 24, 8 and 19. These are numbers that they stand for. The fitness function is the square of this, if you remember. So, square of 13 is 169, square of 24 is 576 and so on. The total fitness of this population is 1170, and the average fitness of a candidate is 293 essentially. So, this is what people observe, that in genetic algorithms the average fitness tends to increase of the population. So, in general the population tends to become healthier. So, the first step, if you remember, is selection, and that is done based on probability proportional to fitness. So, these are the probability values for those 4 candidates. You can see that the candidate with the highest fitness has the highest probability of 0.49. This is just computed by dividing that by 1170, which is the total fitness. So, the expected number of candidates in the selection process is that higher fitness candidates will get a higher number of representation in the cloned population, and we expect that the second candidate will come almost 2 times, the fourth one will get 1.23. This is on the average because these are expected values and so on. The third candidate does not have a great chance of reproducing itself. So, let us say we spin this roulette wheel that we spoke about and produce these candidates. So, we find that the first candidate has got 1 copy, the second candidate has got 2 copy, and the last candidate has got 1 copy, and the third candidate does not exist in the cloned population. So, these are the candidates that we have. We have 2 copies of this second candidate and 1 copy for the first and 1 copy for the last one essentially. So, this is a new population. How does this population look? These are the 4 candidates in the population, and now we do the crossover operation. So, we randomly choose crossover points we randomly pair them and then we choose crossover points and then mix up the genes as we have seen earlier, and what we get is a new population whose numbers are 12, 25, 27 and 16 respectively. Their fitness values are 144, 625, 729 and so on. You can see that it has become fitter than the previous population, and the average fitness has also gone up to 433. So, this new population is fitter than the previous population, where the fitness function is a square of their binary number representation. What happens in cycle 2? So, we have these 4 candidates. The probabilities of selection, as you can see, are high for the middle 2 candidates and low for the other 2 candidates here. So, we expect the middle two candidates to get more representation in the cloned population. In fact, both of them are expected to get more than one copy essentially. So, supposing we do the roulette wheel and we actually get 2 copies for the second candidate and 2 copies for the third candidate, and so our new population looks like this. So, these are 2 copies of the second candidate and 2 copies of the third candidate, and this is what the population now looks like. I have drawn one number in red. Can you guess why is that? So, the total population has gone up, the average population is gone up to 677. So, it is a fitter population, but it is a less diverse population. There are only 2 kinds of individuals left. We started with 4 kinds of individuals, 4 different unique kinds of individuals, and now we are left with 2 kinds of individuals left. The reason I have drawn this in red here is that this particular gene, the third gene, is missing from all 4 candidates essentially. Which means what? Which means that however much churning you do after this, the middle gene will not show up essentially, and the middle gene is there in the optimal candidate. What is the largest value of the fitness function you can get is only if all the bits are 1 each. What this example has shown is that if you work with a small population, then there is a possibility that you may lose out on some genes and the population will become less and less diverse. So, a statement like this is made about, for example, some animal forms. So, the cheetah, for example, it was such a perfect hunter, but it was a perfect hunter in the grasslands of Africa essentially, where it kind of ruled the roost essentially. But gradually as humankind has changed the world, the environment is changing for different life forms essentially. The cheetah became such a perfect hunter that its population become very less diverse essentially. So, the gene variation in the cheetah species is very low essentially, which means that genetic churning will not have too much effect. So, just like these 4 candidates that you see here, any amount of genetic churning will not produce a candidate which is better than this, for example. So, this is the best that we can do with this. And it is said that the cheetah is no longer adapted to the modern world where human beings have removed lot of grassland and things like that, and that danger exists that a species may become less diverse and unable to adapt to the changing environment. Of course, human beings are an exception, but that is probably also because we are cognitive creatures which we manipulate the environment while the others do not so much. But the point that we wanted to make was that a large diverse population is a necessary starting point for genetic algorithms to work with essentially. Otherwise, the population will become very less diverse as shown in this picture here. So, let us sum up with some practical matters about genetic algorithms. Candidates are encoded as chromosomes, which are made up of genes. Genes are like components in the candidate. So, whichever candidates can be represented in terms of many components, we can use genetic algorithms with. They work by inheriting components from 2 different parents. So, we have just kind of followed nature by saying that it is a child is produced by 2 parents, but in practice of course, there is no such restriction. You could have chosen 3 or 4 and still devise genetic algorithms. A careful encoding is needed of the problem solving. So, when we come back, we will look at genetic algorithms. So, GAs is often used, it should be A. So, GAs are often used for many problems, and we will look at how we can solve TSP using genetic algorithms next. And the last observation we made that a large diverse population is critical to the performance of genetic algorithms. So, we will come back and look at how TSP can be solved using genetic algorithms.